All right, so you're going to be adding a few more pages to your lab notebook. If we didn't already do this in class, I don't remember. Go to your next available full page and you'll label it time-dependent forces. You'll copy this stuff down, and then we're going to move on to types of forces after this. Time-dependent forces, you're going to have two techniques and two examples. Technique A and then an example, and then technique B and an example. They're kind of reverses of each other. You should be able to fit this on one page. Technique A is just a little bit longer than technique B because there's some extra steps that need to be shown. Newton's second law, sum of the forces is mass times acceleration. Calculus, we know that acceleration is the time derivative of the velocity as a function of time, and the second time derivative of position as a function of time. So technique A is that if we know information about force, we can divide it by mass to get acceleration, and then we can integrate to get velocity or position. And we've done this once already on one of our example packets, but here we are again. Now you can have an example in your notebook. So for our first example, we've got an object that is 2 kilograms, and at t equals 0, its position is 3 meters, and it has a velocity of -12, and it's experiencing a force of 3t minus 4. This is not a constant force, it's changing over time. So first we'll find the acceleration. We'll take F over m. This is easy, and I split that up into two fractions just to reduce it. I didn't write the units here, but they would be meters per second squared, of course. And you can pause this as needed to copy down everything. So next we got to find velocity and then position. So to find velocity, we write dv dt is acceleration. We're going to multiply both sides by dt. Then we integrate and evaluate. You have to show these two steps where I have the blue items marked. That is the step where you integrate with the limits of integration shown, and then the integrals before you evaluate them. And before you evaluate, you got to put your limits back here again. You'll lose points on the AP test if you don't do both of these steps whenever you're asked to integrate, especially during a derivation. So our velocity at time 0, our velocity was -12. At some later time t, our velocity is going to be v. So the integral of dv is just v. The integral here, we use simple integration because we're just dealing with t to some power. When we evaluate, we do the upper limit plugged in minus the lower limit. In this case, minus a negative is going to give us a plus. And since this is really plus 12, I have to subtract it to the other side to get a -12. So there's our velocity as a function of time. We'll go through the same exact process now to find position as a function of time. dx dt is v. Multiply both sides by dt. Make sure you show both the step of integration and evaluation. And then we'll take this 3 over here and add it over. At time 0, our position was 3. At some later time t, our position is going to be x. And here's our position as a function of time. 3t cubed over 12 minus t squared minus 12t plus 3. So that is all that we have to show for technique A. Let's go on to technique B, which will be a little bit faster. Technique B is if we are given position as a function of time, or velocity as a function of time, or even really acceleration, but that's pretty easy. You would multiply mass times acceleration to get force and take derivatives to find acceleration as needed. So this is what you'll need to show for our next example. I've got the same 2 kilogram object that has a position of the same function we just came up with. So we were working essentially the last problem we did backwards, just to reinforce some of the ideas, make sure we did it right, and to come up with the same force. We'll know we did it right. So what is the force it experiences? Well, we take the time derivative of position, make that exponent 1 smaller, bring it down, or bring it down, then make it 1 smaller. The 3 and the 12 can reduce. We take another derivative. The derivative of a constant term is 0. The 2 and the 4 can reduce. We now got 3t over 2 minus 2 for acceleration. Force is mass times acceleration, so we take our mass, we multiply it by our acceleration, and now we get force is 3t minus 4, which is, of course, the force that we started with. After this, we'll start a new page and we'll label it types of forces. All right, for types of forces, there's a bit of text to go with these. And to speed things up, I put a copy of this text on Google Classroom. And if you'd like, you can print it out and you can cut this up as we go, and you can tape it into your lab notebook. Be careful that you don't use pen or really pencil to write on top of the tape, because that will smudge. So if you're going to do this, cut out the words that you need as you need them, tape them into place. Anything else in here, like formulas and comments and defining variables, you'll have to do that by hand, and make sure that you're not writing on top of the tape, because again, that will smudge. So go print that out now if you need to, and we'll start going over the forces. Again, you can pause as you need to have time to tape things in or to have time to copy things down. So in the universe, there are 4 fundamental forces. That's it. Everything that we have around us, all the complexity that we see, everything boils down to these 4 forces. Amazing how 4 things can create such incredible complexity around us. So there's a nuclear strong force. That is the absolute strongest force in the universe, but it only acts over a very, very short distance. So it dies off incredibly quickly. It binds nucleons together and quarks within nucleons. So this is really like the atomic glue that works at the smallest level to hold things together. Then we have the electromagnetic force. It's a combination of electric and magnetic. Really, they're just 2 sides of the same coin. This force works over an infinite distance. It gets smaller the farther you go out. And in a sense, the nuclear strong force gets smaller as you go out as well. It's just that this one dies off so incredibly fast that it's basically 0 by the time you get an incredibly short distance away from anything. Whereas the electromagnetic force dies off as 1 over r squared. It still dies off, but we notice electric effects at much, much greater distances than any kind of nuclear force effects. We'll go over electromagnetic force more in more detail in just a little bit. There's also a nuclear weak force. This force is responsible for changing one type of quark into another. We're not going to get into that. It's beyond the scope of this class. But it transforms neutrons into protons or vice versa via a process called beta decay. This is responsible for unstable atoms turning into more stable atoms by breaking apart and forming like two smaller molecules, right? Like radioactive decay. This force also acts over an incredibly short distance, although a longer distance than the strong force. And it is the third strongest force in the universe. And the weakest force in the universe is gravity, which may seem absurd because, you know, gravity kind of dominates our lives to some extent. We're stuck to the earth because of it. But if you think about how big the earth is, you need a heck of a lot of mass before gravity becomes an appreciable effect. You know, we can pick up an object with a magnet, and that magnet is able to overpower the gravitational force of the earth. A little tiny magnet can overcome the gravity of the entire earth. So from that perspective, gravity is a relatively weak force because it doesn't happen on small scales. You need a very, very large amount of mass before you notice gravitational effects. In Physics C, we're only going to cover gravitational and electromagnetic forces. All the other types of forces that we learn about, and some of them we've already talked about, tension, normal force, all those kind of forces, they're just applications of the electromagnetic forces that occur on a very, very small scale. We call them normal force, tension, friction, and things like that when we observe them on a larger scale. So moving on, gravity. We're going to look at two types of gravity. One, universal gravitation. That's the force between any two objects that have mass. The equation, the force of gravity, which would be a vector, is g m1 m2 over r squared. There is a vector form of this equation, but it's kind of confusing, so I'm not going to put it down. You'll oftentimes see this equation with a negative written out in front of it. The negative there would mean an attractive force. But this is the way that the formula appears on the equation sheet, and that's the way I'll write it here. So we got the magnitude of the force. This g is a universal gravitation constant, 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. Notice if you take those units and plug them in here and do dimensional analysis, you will be left with units of newtons when you cancel out the meter squared on the top and the kilogram squared on the top and the meter squared on the bottom. It cancels out here. M, of course, is for mass, that's in kilogram. R is the distance between the centers of the objects, that would be in meters. I drew a little picture here. We have two equal and opposite attractive forces on M1 and M2, separated by some distance R that goes from center to center. If you are near the surface of a planet or a moon, we can approximate gravity in a simpler way so that we don't have to use this big complex equation. We approximate gravity as F equals mg. Now this little g is different than big G. On the surface of the Earth, little g is 9.81 meters per second squared. On the moon, it's about 1/6 of that. On Jupiter, it would be greater than that. And this equation really comes from this one. So if we consider mass 1 to be the object on the surface of the planet, and M2 is like the moon or the planet, we can pull that M1 out in front, and then this stuff here is G. And if you were to plug in the mass of the Earth and the radius of the Earth squared and use this value for G, you would come up with 9.81. This G here is representative of the gravitational field vector. It is the force per unit mass, which is also the acceleration due to gravity. But we'll say it's force per unit mass because that's going to be a little more useful in terms of getting your mind in the right place for where we'll be going with electric fields and magnetic fields and electric forces and stuff. M, mass of the object on the surface, and G is the gravitational field vector. it points in the direction that gravity pulls, so on Earth it points towards the center of the Earth. Whenever you see one of these lines in here, please draw a dividing line like that in your notes as well before you do the next thing or tape the next piece of text in or something. That just keeps some of our concepts separated from each other. You'll be in charge of determining how much space you need before you start a new page. Ultimately, we've got somewhere close to 10 forces that we're going to go through, so it might take up a couple pages. All right, electromagnetic forces next. You can see that line that we drew just after gravity. First, we've got the electric force that occurs between two charged objects. This is known as Coulomb's law. If both the objects are positive or negative, the force will point away and it will be a repulsive force. If the objects are opposite in charge, positive, negative, then the force is attractive. And of course, R again is from center to center of the objects. The magnitude of this force is kqq over r squared, very similar to the gravitational force, and we'll do the same trick. We can pull this q out. This would be the magnitude of the second charge. This is Coulomb's constant, the distance between them. And this stuff here is the electric field, which we'll talk about more later. So you could write the Coulomb's law in this way. You can also write Coulomb's law as F equals QE, where E is kq2 over r squared. You'll oftentimes see these as a lowercase q and then a capital Q. So keep in mind, like charges repel, opposite charges attract. F here is the magnitude of the electric force. Coulomb's constant is 8.99 times 10 to the 9th. Newton meter squared per Coulomb square. Coulomb is how you measure the magnitude of a charge. A lot of times we'll just use 9 times 10 to the 9th. That's acceptable. It's like using 10 instead of 9.8. R is the distance between the centers of the charges, and in this equation, E is the electric field, which points in the direction that a positive charge would move. Next up, we've got the magnetic force. So, magnetic forces are exerted on charged objects that move through a magnetic field, and they have to be moving through the magnetic field in a certain way. If they're moving parallel to the field, either in the direction of their field or opposite the direction of the field, downfield or upfield, no force will be exerted on it. They have to be at some angle to the field. The force on the charged particle will be the charge times the velocity vector, and this is not a multiply symbol, this is a cross product. So it's QV cross B. B is the magnetic field vector. V is the velocity vector. We'll talk a little bit more about this later. You don't need to know too much about it now, but I just wanted to introduce it. This is a shortcut to evaluating this cross product. To really evaluate a cross product, you need to use a matrice and find a determinant of a 3x3 matrice. I'll show you an example of that, but it's not something you're going to have to know how to do. We'll use the right-hand rule to figure out the direction, and we'll use this shortcut here to figure out the magnitude. So here you use the magnitude of Q, the magnitude of V, and the magnitude of V, and then theta is the angle between the velocity vector and the magnetic field vector. If you wanted to find the direction of the magnetic force, you got to use the right-hand rule. You'd point the fingers on your right hand straight out, and you'd hold your hand so that your fingers point in the same direction as the velocity vector. Then you curl your fingers on your right hand in the direction of the magnetic field. And you may need to rotate your palm up or down so that your fingers have the ability to curl in whatever direction you're trying to. Then once you curl your fingers in that direction, your right thumb will be pointing in the direction of the force a positive particle would experience. And if the particle was negative, the force will be in the opposite direction of your right thumb. We'll do plenty of this later on. We'll also talk more about cross products when we get to torque, because torque is R cross F. All right, so now you draw another line down at the bottom, go to a new page if you need. After this, we're going to be breaking down individual types of forces that are examples of how electromagnetic interactions manifest themselves on a larger scale. All right, so everything here is an application of an electromagnetic force. These are the everyday forces that we've already been talking about, which are just large scale examples of very small electromagnetic interactions. So I put these in alphabetic order. First, we have the applied force, usually for the force of a person who's pushing or pulling an object via direct contact, and that's just F sub A. Then air resistance or drag. It's a resistive force. That means it's directed opposite of the motion of the object. It's usually proportional to the velocity of the object raised to some power. And the force of drag also depends on the shape and the mass of the object and the properties of the medium through which it moves. All those factors there, the shape, the mass, the medium through which it moves and stuff, those are things that help determine this constant K and this value A. So F is the magnitude of the force. K would be the drag constant. You oftentimes see B used as well for that. I don't like to use B because it gets confused with a 6. V would be the velocity, and A is the power the velocity is raised to. For our purposes, mathematically, A is usually going to equal 1 because that's simpler mathematically to work with, although we will look at a couple examples where A is not 1. Next type of force, kinetic and static friction. Kinetic friction, also a resistive force, so it opposes motion. It's proportional to the normal force that exists between the two objects, and it depends on this value of mu here, depends on the material that the surfaces are made out of. So we got our magnitude of friction, our coefficient of friction, and then the magnitude of the normal force between them. You will also sometimes see this formula with a negative there. Again, that negative would just mean, it's a resistive force, and it's in the opposite direction of motion. You can abbreviate this as just FK. And be careful with these mu's. You need to have a little bulb down there and a little curl on the other side. Take your time when you're drawing them because you don't want them to get confused with something else. And of course, Fn, you could just write that as a capital N as well. There's some options to these. Static friction is a resistive force that prevents objects from sliding, almost like they're stuck together for a moment. Both of these types of friction here are due to small variations in the surface, little bumps on the surface that run into each other as the surfaces try to move against each other. Little hills that kind of stick together and resist moving against each other. So this force always points opposite the direction that the objects would want to move, and it's not always obvious which direction they would want to move. You'd have to use Newton's second law to figure that out. It's also proportional to the normal force. It also depends on the materials the surfaces are made out of. If you change one surface or the other, it will change mu. Static friction, unlike kinetic friction, will adjust itself in magnitude until it reaches a breaking point where the surfaces will begin to slide. So this value here is the maximum value of, mu s times N, that's the maximum amount of static friction. You can't have more than that. Mu S is the coefficient, and N, magnitude of normal force. Pretty straightforward. You've seen this before. All right, last page. This should go a little bit faster than some of the early ones that we did. Normal force, support force of a surface. It's always perpendicular to the surface, and it's not always equal to the force of gravity. We've seen some examples of that already. You could call this N or Fn. Tension, force in a rope, wire, line, cord, string, chain, or any similar other item. It's always the same in simple straight sections of the rope, but tension doesn't always have to be the same within a rope if the rope is doing something complicated like running over an edge, or if it's going over a pulley or something like that. The friction between the rope and the pulley, or the rope and the edge, can support some of the tension between one section and the next, resulting in unequal tensions in different portions of the rope. If your rope was curved or something, tension would not always be equal in a curved rope as well. Next, spring force. I believe the spring force may be the very last one that we look at. So a spring force is a force that's due, I forgot to write that in here, a force due to an object's distorted shape. This happens when you bend an object, but it could also be due to stretching or compressing it. In general, the force is negative K times our displacement raised up to some power. The negative there symbolizes it's a restoring force. We have a constant. This is our displacement. Most of the time, you won't see this A there. It would be a 1, and you won't see delta X. It will just be X. We might use this occasionally, and I've seen this on AP tests before, where you have a non-linear spring. So it may be proportional to like the square root of the distance, or the distance cubed, or something like that. In general, though, this is what we'll use. Make sure you don't get this confused with static friction, FS. So if you were using these in the same problem, you might do something like FS and then FST or SP or something like that for force of spring. This is what we'll use to model most of our springs, and those are, I think, all of the forces that we'll need to be dealing with for this semester and next. Thanks for hanging in there, and we'll see you in class soon.